As you can see, fractals and heavy tails on the Romanian stock market. Daniel Traian, Irina Mazurenko, Marinescu.
Thank you. Thank you very much for this invitation. This workshop is a special opportunity for exchanging idea for me, old and good friends, and also to present some research idea. This is actually only an idea. We will develop a real paper. It's about fractals and heavy tails on the Romanian stock market. This is the outline. Why fractals? Why heavy tails? Let's say in the past 30, 40, maybe 50 years, the paradigm, the official paradigm of the financial modeling was the efficient market hypothesis, coming from, let's say, from Samuelson, even from Keynes, but was Fama in the 70s who give that famous definition of an efficient stock market. And during the years, a lot of academics, researchers started to have doubts about these concepts. Are the markets really efficient? How can we reconcile the existence of bubbles, let's say speculative bubbles, with the concept of market efficiency? How do we explain the so-called black swans? Because if the market is purely efficient, if the stock prices are purely random, let's say according to a random walk model, it's, let's say, difficult, if not impossible, to explain the presence of very large variation in the stock return. So, in the 90s, a concept which was initially developed by Mandelbrot in his fractal geometry of nature, was embedded in fractal market hypothesis. And we wanted to test this hypothesis for the Romanian stock market. Another big issue for the last, let's say, 200 years was the normal distribution used in all kinds of fields, not only in economics, but also in physics, in social sciences, in biology, and so on. If, let's say, the distribution of the stock returns is normal, then the probability of having extreme values, let's say large negative returns or large positive returns, it's very small. It's something like 10 to minus 23 or something like this. But events like this happen more often than according to the normal distribution. And one solution to modeling stock returns using Gaussian distribution is to use stable distribution, which is the kind of generalization of the normal distribution. And we will also use this. And also using fractals, using stable distribution, we want to estimate an uncertainty index in order to explain the likelihood of extreme negative returns. Because, of course, stock market is clearly dominated by uncertainty. We can measure uncertainty using entropy coming from physics, and this is not something new. There are a lot of papers dealing with entropy in the stock market, but we could use also those two measures, first exponent and tail index of a stable distribution, in order to characterize uncertainty. The link between these measures of uncertainty and the likelihood of extreme negative returns was made using a Lockheed model, a binary logistic regression. I will show you. I highlighted here only 3 papers. There is one in 2010. Stock markets are seen as complex systems, and all the metaphors coming from physics are described there. The seminal paper of Pitesti about fractal market hypothesis, and also another one about multifractality in the stock market. Actually, a fractal, what is a fractal? Have you seen a fractal before? No? No? Do we have internet here?
No, I'm sorry, we don't have that. But you can try. There is
You can use
internet,
examples
it's
from A
wireless.
Beautiful Mind. Maybe the movie has been seen by most people.
No. There is a set. There is a Mandelbrot set. Yes, it's an artificial. Actually, all the fractals are artificial. Yes. A fractal is a form, a complex form, defined by self-similarity. Let's say a part of the object is a copy or reflection of the entire object. And also has to do with the, let's say, beauty. If you see fractals around or on the computer, you will see how beautiful they are. How can we model this thing using a mathematical model? There is a so-called, a well-known model, the fractional Romanian motion. And there is a number, the Hurst coefficient, which defines the, let's say, fractal dimension of a time series. This number is between 0 and 1, and if we apply, if we estimate this number for a time series of stock returns, we have 3 cases. If the value of this number is 0.5, then the prices follow a random walk process according to the efficient market hypothesis. If the value is lower than 0.5, then we have a so-called persistent series. If it's higher than 0.5, we have anti-persistent series. Actually, if h, the Hurst exponent, is 0.5, the prices are moving completely at random. If it's below 0.5 or higher than 0.5, we can see in the stock market the existence of local trends. So we can anticipate, we can say estimate the probability, the likelihood of having large negative or positive returns. Okay? Good. In terms of stable distribution, like I said before, stable distribution are a generalization of the Gaussian normal distribution. They allow for skewness, they are heavy-tailed, the probability in the lower and in the upper tail are much higher than the ones for the normal distribution, and more any linear combination of stable, independent variables is also stable. So the shape of the distribution is preserved under linear transformation. For the normal distribution, we can write down the probability distribution function. Yeah. In general, for a stable distribution, we know only its characteristic function, because only for 3 distribution we can we know the analytic form of the probability distribution function: the normal distribution, Cauchy distribution, and Levy distribution. Anyway, such a distribution has 4 parameters, and we are interested in this one, alpha, so-called tail index or characteristic parameter. For normal distribution, the value is 2. So if alpha is, let's say, is closer, when alpha is very close to 2, the distribution is very close to the normal distribution, is bell-shaped. Also, this tail index is related to the probability in the tails. When alpha is lower than 2, the probability in the tails of the distribution is higher. So when we apply this, let's say, this model to the distribution of returns, if we obtain for one market an alpha of 1.5, for another market alpha of 1.9, the first one has a higher probability of having large extreme returns, large negative returns. This is the model we are using to correlate the probability of large negative returns to the Hurst exponents of the fractal dimension and the tail index, the probability in the tails of the distribution. This is a binary logistic regression. We define Y being 1 for all the returns in the left tail of the distribution, 0 otherwise. And we are trying to estimate various combination of those two variables. We use daily data for the main index of Bucharest Stock Exchange, that index. Covered, the period is not 2007, is 1997. We have more than 3,000 observations. We estimated the Hurst exponent and the tail index based on a rolling window of 250 trading days, which is an average trading year. The Hurst exponent was estimating using the classical scale range analysis. For tail index, we use a time series regression based on Kutu-Levis method. This is the Hurst exponent for that index over time. So basically, if H is very close to 0.5, there is no room for predictability. Okay? The prices are completely random. If the Hurst exponent is, let's say, around here, 0.9, then in the stock prices of returns, we can see some local trends persistent. If H is around, let's say, 0.3, the series become anti-persistent. There are still local trends, but they tend to revert very quickly. So, if we could find, let's say, some periods where the Hurst exponent is significantly different from 0.5, we can, let's say, define some windows of predictability. And using those windows, we can link, using a logic model, and we can estimate the probability, let's say, of having a stock market crash. This is the utility. The tail index, that number that evaluates, quantifies the probability of tails, it's much more stable, let's say, than the Hurst exponent. You can see, since 2007, the value was around 1.5, 1.67, which is lower than 2, the value for normal distribution, but yet there are some variations here. Starting 2007, 2008, with the beginning of the financial crisis, the value of alpha, the tail index, is on average around 1.7, meaning that the probability of having large negative returns was, let's say, constant since 2007, 2008, but still far from normality. These are the results from that binary logistic regression using only the first exponent as explanatory value. And we can see there is a negative relation between the probability of having a, let's say, stock market crash and the value of the first exponent. Higher the first exponent, higher the, let's say, the fractal structure in the stock market, lower the probability of having a stock market crash. We try to estimate also a model with the tail index, but the tail index doesn't have a significant impact on the likelihood of extreme negative returns. So what we are trying to do now is to set up an uncertainty index. We want to aggregate actually three-dimensional fractality using first exponent, probability in the tails using tail index, and maybe, let's say, entropy of probability density function of returns, or entropy of the distribution function of returns. We want to set up an aggregated indicator, and we want to see the connection between this uncertainty index and the probability of having a crash. At this stage, the aggregation is simple. We just multiply first exponent with the tail index. This uncertainty index, as we define, takes values between 0 and 2. The equilibrium value is 1, because we have, let's say, alpha must equal 2 for normal distribution, and h must be 0.5 for the random walk model. Any departures higher than 1 or lower than 1 are a sign of increasing or decreasing uncertainty. And if we could link those variations with the probability of having a crash, this may be a sign of predictability. These are the results of the model. The probability of having a stock market crash is also negatively correlated to the uncertainty index defined using the first exponent and the tail index. So, there is room for improvements. We can try to, like I said before, to include the entropy as a part of this aggregation. We can try to use other kind of model. Why not? We try to estimate the quantile regression using the distribution of returns and taking into account only the 1% of 5% lowest values of the return distribution, but still the result needs to be defined, let's say. Anyway, using only the fractality dimension and tail index of stable distribution, we could see a clear link between uncertainty index and the likelihood of stock market crash. Thank you.
I must thank you again. And we hope we have all the 2 papers, because there are 2 papers now. And if you send us soon, that will be very interesting, because you can see online. Now I must say that we have another 6 papers. I have 3 papers on my desktop, but I think it's enough. We must go to it. We must go to discuss. And I must thank you, to all of you, because it was indeed meet between friends. That is the idea. This is Eden, in fact. This is our, let's say, family now. And I must thank you again. Holland. Vă rog frumos să rămâneți toți participanții care au expus lucrurile, pentru că mergem împreună să stăm de vorbă, da? Să facem ceva proiecte de viitor. Mulțumesc frumos!